we'll go for electromotive force, which is called EMF. An EMF is an electromotive force with same unit as voltage, and it is the driving force that moves charges in a wire. You can observe a image over here. In this image, a wire is coiled, and in this wire, a magnet is induced in this coil. And we observe in the voltmeter, as the meter moves towards as the magnet moves towards the coil, the voltage increases, whereas when the magnet moves away from the coil, the voltage decreases. An EMF applied to a conducting wire drives electron that creates a current in the wire. This statement can be very well explained in the following figure. Here you can observe what is actually happening. We have a coil, that is a wire, which is connected to a meter, and in this coil, when the magnet is induced, a shining glowing points can be observed, and these are nothing but the electrons. And more number of electrons can be observed when the magnet is introduced in the coil, and these electrons makes current to flow through this wire. And on this electromotive force, we can understand Faraday's laws of electromagnetic induction. Basically, electromagnetic induction is on electromagnetism. Here, the magnetic field interact with the electric circuit to produce an electromotive force. This phenomena is known as electromagnetic induction. Now we are going to study Faraday's law. Here we are going to study first law as well as the second law. So first of all, we'll see what is Faraday's first law. If suppose you have a magnetic field which is due to the magnet, and this magnetic field changes. If a coil is there, and if magnetic field is changing, then EMF is induced in the coil. Okay, we have a coil made up of wire, and while introducing the magnet or moving the magnet towards and away from this wire or a coil, will induce the EMF in this coil. This EMF induced is called induced EMF, and if the conductor circuit is closed, the current will also circulate through this circuit, and this current is called induced current. So, in this first law, what we understood that if we have a coil of wire, and in this coil, if the magnet is moved away and towards this coil, then what will happen? The magnetic field will change, and due to this change in magnetic field, the EMF is induced in the coil. This is nothing but the Faraday's first law. Okay, now we'll see the second law. What Faraday's second law states? It states that the magnetic field or the magnitude of EMF that induced in the coil is equal to the rate of change of flux that linkages with the coil. The flux linkage of the coil is the product of number of turns in the coil and the flux associated with the coil. So this second law is very clear that EMF induced is directly proportional to the rate of change of flux. Here we will switch to the derivation for Faraday's law. What we have done? We have considered a coil, inducting coil. Let it be L, and I is denoted for the current flowing through the circuit. V is the potential. And suppose we consider the two instant of time, that is T1 and T2. So for time T1, the flux linkage with the coil is N into phi1. Phi is what? Is flux. N is the number of turn. And for the instant of time, we are considering T1 is the time instant. Similarly, for another period of time instant, that is T2, the number of turns N we are not changing, so it is N only. It is constant for both the instant, that's why the number of turns is N, and phi2 is the flux. Okay, phi2 is the flux for time instant, time T2. Now, for the next equation, we can have change in flux linkage, that is change in flux can be written as N phi2 minus N phi1. So we can take out the N as constant and it is N times phi2 minus phi1 is the change in flux linkage. Now, this phi2 minus phi1 will take it as phi. So, the change in flux linkage will be N into phi. And what will be the rate of change of flux? Rate of change of flux will be N into phi by T. And suppose we take the derivative of this, it will be N into d phi by dt. So, we can write the rate of change of flux linkage is N into d phi by dt, and this is nothing but EMF. So, we have the final equation as E is equal to N into d phi by dt. Now, the question arises, how we can increase the EMF that is to be induced in a coil? The first thing is by increasing the number of turns in the coil, that is N. We have seen the coil. If suppose the number of turns of this coil is increased, we can increase the induced EMF. One more thing what we can do, we can increase the strength of the field, that is the magnetic field. If we have the magnetic field strength very high or greater than, or we go on increasing the strength, that also increases the EMF which is to be induced in a coil. One more thing we can do is, if the speed of relative motion between the coil and the magnet is increased, then only we can increase the EMF that is to be induced in a coil. We have seen earlier, a coil is there, a magnet is there, and what we had done, we had introduced the magnet inside the coil. It shows that the EMF induced, and when it comes out, the voltage decreases. So if the speed of introducing that magnet in the coil is increases, then also we can increase the EMF that is induced in the coil. So these are the 3 points. By using these 3 points, we can increase the EMF that will be induced in a coil. Now we'll see the application of Faraday's law. These Faraday's law can be used in power transformers. The basic working principle of electrical generator, there also we use Faraday's law. In induction cookers, we require Faraday's law. Electromagnetic flow meter is used to measure the velocity of certain fluids. Even in this electromagnetic flow meter, we require to apply the Faraday's law. Faraday's law is used in well-known Maxwell equation. By using Faraday's law, we can derive Maxwell's equations also. It is also used in musical instruments like an electric guitar, also in electric violin and many more musical instruments. Now we'll see Lenz law. What actually Lenz law states? We have studied Faraday's law. Lenz law is similar to Faraday's law, but the only thing we need to introduce a negative sign. In the equation, E is equal to N into d phi by dt. This we studied in Faraday's law. What Faraday's law states? E is equal to N into d phi by dt. So what we need to introduce? We need to introduce a negative sign, and that will states as E is equal to minus N times d phi by dt. This is your Lenz law. Now we'll see the statement, what the statement says. The induced electromotive force with different polarities induces a current whose magnetic field opposes the change in magnetic flux through the loop in order to ensure that original flux is maintained through the loop when the current flows in it. In this, you can observe an image where you can see a magnet is there and magnetic flux is produced in the coil, and in this magnetic flux in this coil and this magnet, you can observe magnetic field is opposing the change in magnetic flux. They are not in the same direction. Now we'll see some of the applications of Lenz law. Lenz law is used in eddy current balance. It is used in metal detectors, eddy current dynamometers. It is used in braking system on trains, AC generators. It is also used in card readers and microphones. With this, I stop.